Let me just repeat what I said in an email just an hour ago, that this and tomorrow will be our last colloquia at the Black Hole Initiative for this spring semester. Today is the last BHI colloquium that will be given by Netta Engelhardt. She's next door at MIT, and if you have additional questions, of course, you can ask her afterwards. She will be around. And tomorrow we have a talk by Stephen Wolfram about his new theory of everything. And we look forward to that. That will start at 2 p.m. And without further ado, maybe I should ask Fabio to introduce Netta again.
Yes, so today we have the pleasure to have Netta Engelhardt. She's an assistant professor of physics at the MIT, as Javi just said, and she works on gravitational aspects of quantum gravity with an emphasis on string theory. And today she's going to talk about the black hole information paradox in the age of holographic entanglement entropy. So please go ahead, Netta.
Thank you very much for the invitation. It's a pleasure to be back, as much as I can be back when I'm actually talking from a different location. I hope everyone is doing well. So today I'm going to talk about the black hole, the information paradox, the information frontier, and in particular about these recent developments that have been going on for the past year that are a consequence of our understanding of some aspects of holographic entanglement entropy that have allowed us to make progress on the frontier of the black hole information paradox. So it's very exciting in this field right now. So it's a real pleasure to be able to give a talk on it. And please interrupt me with questions if you have any questions during and also after. So I'm going to begin with a little bit of motivation, the what and the why. And I'll do my best to keep this talk at least relatively self-contained so that we'll spend some time giving background on the information paradox itself. So the information paradox, the black hole information paradox, is an apparent contradiction between the predictions of semi-classical gravity and the unitarity of quantum mechanics. It's one of the most long-standing paradoxes in physics, which in some sense makes it extremely exciting because we know physics has to work. So when there's a paradox, that's something that's telling us that our attention is needed on that. It's something that we need to understand better. And it's also somewhat frustrating because it's been around for so long, since the 70s. So a 5-second overview of what's going on with the information paradox, and I'll spend a lot longer afterwards explaining it in more detail. We can imagine we have Alice and Bob with entangled particles, and Alice ends up falling into the black hole, and Bob doesn't. And we do a semi-classical gravity analysis, which is to say an analysis where we treat gravity as being weakly coupled to quantum field theory. And that's Hawking's analysis, which implies that information is lost or evolution is non-unitary. So this is the rough setup, even though this is of course far too simplistic to actually reflect what's really going on. Now, at the root of this apparent contradiction between the predictions of semi-classical gravity and unitarity is really our ignorance about the behavior of strong quantum gravity. So strong quantum gravity is critical for our understanding of the black hole interior, and we expect that the information paradox is a consequence of our ignorance of this fine-grained physics of quantum gravity. As I mentioned earlier, ultimately paradoxes are indications that we're thinking about something in the wrong way. Our framework is wrong. We're not looking at it right. And so the information paradox has a lot that it can teach us about quantum gravity. And that's with a caveat that it can only teach us about quantum gravity if we can get insight into it without having a direct formulation of quantum gravity. Of course, if we don't, then we have a bit of a catch-22 where we'd like to use the information paradox to learn about quantum gravity, but to actually resolve the information paradox, we need quantum gravity. So there's a question of how much it can help us, but if we can get insight.
Well, it looks like we lost Netta. Fabio, or Nicole, can you figure out what happened?
Yeah, I think it's just the connection with Netta that is out. Because I see other people moving like in the screens. So
okay, let's just wait a second. Does anyone have? Okay, so now she's lost.
the fire truck is mine.
Does anyone have a cell phone number for her?
No, I'm emailing her now, Avi, telling her to come back on if she can.
Yeah,
okay.
she's back. She's back, it seems.
All right. Is everyone back? I'm back.
Yeah, we lost you. Something with your connection must have been.
It might be. I switched the network, so hopefully this should be fine now.
Okay. Let's put your slides back on.
Yeah. Yes, are we good now?
Yes, everything's fine.
Great. Yeah, so I was just saying before we got interrupted by the internet that having a paradox is something that could be extremely useful or less than useful depending on whether we can get any insight into it without having a full direct formulation of non-perturbative quantum gravity. So a little bit about the information paradox. So the information paradox has a history of long periods of relative silence and short periods of frantic activity following a breakthrough or development. When I was a graduate student, Joe Polchinski summarized it for me. That the information paradox is described working on it as long periods of boredom punctuated by short periods of frantic activity. I think he was quoting Hemingway, but I don't think Hemingway was talking about the information paradox. So examples of such breakthroughs or developments, we have Hawking's original work, Page's results, the Firewalls results from 2012, Hayden Preskel, and also the new developments starting with May of last year with the paper that I wrote with Ahmed Al-Mhairi, Don Meroff, and Henry Maxfield, and a paper that came out the same day by Jeff Pennington, which these two were coordinated since there was a significant overlap between them. Now, there's a rather significant qualitative difference, I would say, between the results prior to this past May and the results of May, these breakthroughs. So before the May results for the 2019, a rather broadly accepted viewpoint, not universally accepted, but broadly accepted, was that the evidence of unitarity of black hole evaporation, and evidence of information conservation, would require some very strongly coupled quantum gravity calculation. And semi-classical gravity, it just looks like it's losing information. That's what happens at the level of semi-classical gravity. And a lot of these older results were sharpening the paradox or asking if it were unitary, if evolution were unitary, what would we see? What would be the signatures of that? The new developments are different, qualitatively speaking, in that the new developments are a purely semi-classical analysis that is indicative of information conservation. So it's a step forward in a way, in a sort of different type of step forward than we've had before. And I think it's safe to say that most of us, certainly I, thought that this was impossible, that we could not see evidence of unitary evaporation purely at the semi-classical level. Now, I should qualify. I say purely semi-classical level, and it's not 100% accurate. So it's a semi-classical analysis, but it is motivated by an insight from quantum gravity, in particular holography, or as I will say later in the talk, the gravitational path integral. So it's there's a small injection of quantum gravity information in there, which is what makes all of this possible. Okay, so the outline of this talk, I'm going to give some background on the black hole information paradox. Andy, was that a question? I think you're muted.
Sorry.
Yeah.
I guess an exception to that would be the old calculations of pair creation, which showed that the semi-classical calculations, which had a factor of e to the entropy, not twice the entropy.
That's right.
Which was a semi-classical analysis that showed that was indicative of unitary.
It is indicative. You're right. I should have mentioned that. That's right. I suppose you could say, is this e to the minus, that a really perturbative correction? It's really a kind of a non-perturbative correction, but I agree with you. This in the same spirit. And this, the gravitational path integral calculation here that I will talk about at the end really does show that you do need to talk about these exponential corrections. So I agree with you. So the outline here is I'll give some background on the black hole information paradox, sort of a maybe somewhat historical perspective on how we got it. And then so that's the first half of the title, the second half of the title is the age of holographic entanglement entropy. So I'll talk a little bit about what that is, what is holographic entanglement entropy, the salient points of that. And I'll put those two together to what's been happening this past year on the black hole information front. And I'll finish with what I think is going to happen tomorrow, which is certainly colored by what I'm working on at the moment. So I'm going to start a little bit earlier than maybe people usually start when they talk about the black hole information paradox, which is Wheeler's Gedankenexperiment and the advent of black hole thermodynamics. So this, the cartoon, and I'm glossing over a lot of the details of the Wheeler T Gedankenexperiment is the following. So if a black hole has a classical black hole in GR, if it has no microstates, then it has no entropy. And so if you take a hot cup of tea, which certainly has entropy, you throw it in the black hole, then you decrease the entropy of the universe. And that seems to be in contradiction with the second law of thermodynamics. So I can't quite say this as well as Sir Arthur Eddington, so I'll just quote Sir Arthur Eddington. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There's nothing for it but to collapse in deepest humiliation. So we would prefer not to have GR collapse in deepest humiliation. We really like GR. So this was proposed by Jacob Bekenstein, that in fact black holes are thermal objects. They have a temperature and they have an entropy. And this thermodynamic entropy is due to quantum gravity microstates, and is given by the area of the event horizon over 4g h bar. To be fair, he didn't quite guess the factor of 1/4. That analysis was done later by Hawking, which is why we call this the Bekenstein-Hawking entropy. So for a black hole close to equilibrium, we expect the temperature of asymptotically flat black hole, which is proportional to inversely proportional to the mass of the black hole. This, I should say, this was strongly motivated by the Hawking area theorem, which tells you the area of the event horizon increases as you fall forwards in time, as long as you're talking about classical gravity and positive energy conditions, and the Bardeen-Carter-Hawking analogy of black hole mechanics to thermodynamics. Now, at the time, everyone thought that this was an analogy rather than an actual statement of the thermodynamics of black holes. And there was a reason for this, which is that black hole thermodynamics, strictly speaking, doesn't make sense as more than an analogy if you're strictly in the classical limit. Because if black holes had temperature, then they'd have to emit radiation. And black holes in general, in GR, are literally perfect absorbers. So this analogy was nice, but it looked like it was just going to be an analogy. It's critical to consider quantum corrections in order for this to be anything more than an analogy. And in fact, the proportionality constants for the temperature and the entropy, the 1/4 in the A/4gh bar, was fixed by a semi-classical analysis that Hawking did. So this was critical for fixing those constants and for having this black holes as thermal objects actually make sense, because they are not perfect absorbers once you consider quantum corrections. Now, what do I mean by quantum corrections? I want to be somewhat precise about this. So what I mean by quantum corrections is that we're working in a semi-classical expansion. So here I've written the metric down as an expansion, where this here refers to a power of gh bar. So the small parameter in our expansion is gh bar. G Newton is Newton's constant multiplied by h bar. And what we are doing here is we're writing a perturbative expansion. And the way we're getting it is the following. GAB to the 0 is a classical metric that solves the Einstein equation with classical matter. And then we can consider quantum fields propagating on this classical background. We can take those quantum fields, once we've solved for them on this background, we can plug them back into the stress tensor, and then we can calculate the correction on GAB0, which gives us a quantum correction, the quantum back reaction of these quantum fields. So we can keep on doing this iteratively to get progressively higher terms in this expansion. And as a footnote, I've written this down in terms of whole powers, integer powers. You can actually get fractional power contributions from quantized gravitons, but that's a whole other story. Qualitatively speaking, this is how this works. So there are a couple of different regimes here, and I'm going to give them names just so it's not confusing. When I say classical gravity, I mean we're working at order GAB to the 0, and we mean there are no quantum fields in the problem at all. We're not considering them. We're not considering even no backreaction, just no quantum fields at all. When we say quantum field theory on a curved background, what we mean is we're still working at order GAB to the 0, but we're considering quantum fields that are propagating on this background, but we're not considering GAB to the 1. We're not considering the back reaction of these quantum fields. And when we say semi-classical gravity, without any qualification, generally mean that this expansion to any order. So basically it means we're including back reaction of the quantum fields. So these are the 3 terms that I'll be using here, and we'll go back and forth between them depending on the regime we're interested in. Okay, so back to black hole thermodynamics. We know we're working in semi-classical gravity now, so we're working in this perturbative expansion. And what Bekenstein proposed is that the total entropy of the universe, which is to say the entropy of the black hole, so that's area over 4gh bar, plus the entropy of matter outside of the black hole, would always increase. And that's this quantity here that he called the generalized entropy. And people these days are saying it should really be called the quantum corrected area, but we'll stick with historical names, just the generalized entropy. And this SVN of out sigma is what is known as the fine-grained or entanglement entropy of the quantum fields outside of sigma. I'll define this more precisely in just a moment. So here we have, this is meant to be a Cauchy slice of our space-time. The surface sigma here splits the Cauchy slice into 2, an outside and an inside. And the generalized entropy of sigma is, this von Neumann entropy over here computes the entropy of quantum fields on the outside of sigma. Then the generalized second law, it's just a second law of thermodynamics that includes gravity, is the statement that when sigma is a cross-section of the event horizon, the generalized entropy increases as a function of time. So I have a picture on the next slide. So here we have a black hole, and here we have an event horizon right there. And we have 2 cross-sections of the event horizon. This is out sigma 1, out sigma 2. And the generalized second law is just a statement that the generalized entropy of sigma 2 is larger than the generalized entropy of sigma 1. And again, this includes the gravitational entropy, the area term, and the entropy of the matter fields outside of sigma. So this is the second law of black hole, the second law of thermodynamics, including gravity. And this is one aspect of black hole thermodynamics. And it's clear here that it's very important that we have included the quantum field contributions. Now, as it happens, Hawking actually didn't initially buy Bekenstein's story. My understanding of this, which is, I suppose is in some sense hearsay, is that he set out to do a calculation that would show that this was actually just an analogy. And he ended up not showing that, he ended up showing the opposite. So to prove Bekenstein wrong, again, this is my understanding historically how this happened, he set out to compute the putative temperature of the black hole. And if you read the paper, it's frankly a dizzying number of Bogoliubov transformations, which I'm not going to go through here. But the essence of it is that he showed that a quantum field theory on a stationary black hole background, if you have a quantum field theory on a stationary black hole background and you measure the state at infinity, you measure the spectrum, you find that it's thermal with a temperature 1/8 pi m. And that allowed him to fix the coefficient in front of the A over GH bar that Bekenstein proposed as 1/4. So just using standard thermodynamic relations. So this was, and it's really a stupendous analysis and very carefully done, which in some sense left us with no doubt that black holes really are thermal objects and do have a temperature. It leads us also to the case of the evaporating black hole, which is a central player in the black hole information paradox. So if the temperature of a black hole is hotter than its ambient surroundings, and a black hole is truly a thermal object, then it should radiate. And as it radiates, it shrinks in size, it loses mass. But because the temperature is inversely proportional to the mass, as the black hole evaporates, it gets hotter. So it just keeps on evaporating until it's completely gone. This is true in asymptotically flat space. So this means that we can start with a black hole, and the black hole can radiate and eventually disappear altogether. Now, some numbers to ground us as far as what kind of temperature ranges we're looking for. So Sagittarius A star has a Hawking temperature of about 10 to the negative 14 Kelvin. So it's completely negligible. If we're looking at a black hole of solar mass, the Hawking temperature is about 10 to the minus 8 Kelvin, which is negligible compared with the cosmic microwave background. If we want something which is, say, comparable to the cosmic microwave background, we'd be looking at a lunar mass black hole. And if we want something which is particularly relevant to today's day and age, a coronavirus-sized black hole is approximately at room temperature. So this would be a black hole of about 10 to the minus 7 meters across. I'm sure that there's some conspiracy theorists out there who would be very interested in this. So these are just some numbers to ground us, and in terms of the temperatures at different sizes of black holes. Okay, so where's the paradox? So we've set this up, we have an evaporating black hole. Let's take a closer look at it. So this is the Penrose diagram of an evaporating black hole. And I've drawn two time slices. There is a time slice that's way in the past and a time slice that's after the evaporation, sigma prime. The paradox is what appears to be information loss between the state on sigma and the state on sigma prime. And so to see this, to understand what this means and to see this information loss, it's useful to talk about the entropy of the Hawking radiation. So I'm going to talk about a dramatically oversimplified model, and then I'll explain what the actual story really looks like. But this dramatically oversimplified model is actually somewhat useful for understanding the situation. So let's take an entangled pair, the Alice and Bob that we had before, where we have, say, the left particle falls across the horizon and the right particle just makes off to infinity. We're going to take this to be an entangled pair, so the Bell pair, let's say. So the total state of the two looks like this. And we can describe the right particle by itself in terms of a density matrix. It's not in a pure state. We can't write it down as a vector, but we can write it down as a density matrix, a density operator. So this is if we trace out the left particle, the one that fell into the black hole, and we just look at the right particle. Its density matrix is proportional to the identity, which means that it's maximally mixed. Now let's talk about the entropy. So this is this entropy that we saw before. I'm going to now define it more properly, this entropy we saw over here, and talk about a few properties of it. So for a density matrix rho, the von Neumann entropy, also called the entanglement entropy, also called the fine-grained entropy, is defined as minus trace rho log rho. There are a number of properties that are of this object that are very useful. The first is that it's invariant under unitary evolution. It vanishes for a pure state and for a pure state only. So in other words, if we can write our density matrix in this way, if it's just a pure state psi, then this is going to be 0. And it's bounded from above by the thermal entropy, which we call the coarse-grained entropy. And these three properties are going to be quite useful for what I'm about to say next. So what do we mean by information loss? There's a technical and correct way to think about it, but there's also some nice intuition that we can use. So there's some very rough intuition. We can quantify in a rough way the information in a state in terms of the difference between the thermal entropy and the von Neumann entropy, in the coarse-grained entropy, the maximum possible entropy, and the actual entropy, the actual fine-grained entropy of the state. So this is a very rough way of quantifying the information in the state. Now, the thermal state is at equilibrium and essentially has no information content. Again, this is roughly true. And so if a system evolves to progressively larger von Neumann entropy, we say that information is lost, because progressively closer to the thermal entropy, information is lost. An alternative way to think about it, if you don't like that perspective, again, this is all just intuition. If we think of a pure state as the entire system, so this is simply because if you have a mixed state, we can always purify it by adding an additional system, then the von Neumann entropy serves as a rough guide for how short we are of having the full system. Now, of course, this happens all the time. The von Neumann entropy increasing with evolution happens all the time. In tabletop experiments, whenever we have an open system, it will generally interact with its surroundings, settle down to some thermal state, and lose information along the way. And that's because open systems don't evolve unitarily. But the entire universe is not an open system. We don't expect that the entire universe is an open system, and we expect that, therefore, if our intuitions about quantum mechanics are correct, that the universe should evolve like a closed system, which is to say the total von Neumann entropy, the total entropy, should be constant. So now let's go back to our very simplistic model of the EPR pair. So the initial state of the pair is pure. It's a pure state, this state psi. And remember, one partner fell into the black hole, disappeared, then the black hole evaporated. We're left with just one, with just the right particle, which has non-zero entropy. So the entropy went from 0 to log 2. And so the entropy has increased, and the system was not evolving unitarily. Now this is just for the EPR pair, and of course you can say all kinds of words like, well, we really are talking, the EPR pair is certainly interacting with this environment, and there are many issues with this model, but at the end of the day, the flavor here is correct. So let's talk about it a little more accurately. We can imagine forming a black hole from a pure state. And so the universe starts out, the entire universe starts out in a pure state. And Hawking's analysis in semi-classical gravity shows that after the black hole has finished evaporating and all we have left is just radiation, then that state is not pure. So we've started out with a pure state. Then we, at some point along the way, we had two systems. We had the black hole and the radiation. And then we're interacting, and that's okay. Neither one of them has to have entropy, which stays constant because they're both open systems. But eventually the black hole goes away altogether, and the entire system that's left is just the radiation. And so if we started out with the entire system being pure state, and ended up with the entire system being a mixed state, then the system was not evolving unitarily, and we've lost information. So this is a plot of what Hawking, the Hawking calculation shows as far as the entropy. So the entropy of the radiation starts out at 0, essentially before the black hole starts to really evaporate, and then it increases until the black hole has finished evaporating, and eventually it plateaus here to this thermal value. And so since here, the radiation is the full system, it should not have a non-zero entropy, at least not if the system is evolving unitarily. So as I said before, initially before the black hole starts evaporating at 0, then it increases, and the increase is okay because it's not the entire system. But once it becomes the full system, then it had better go back to 0. Give me a moment to read that since I just said it. All right, so that brings us to the discussion of the page curve. So we have a pure state in a closed system which evolves to a mixed state, and information appears to be lost in this curve that I have on the slide right here. So is quantum gravity actually non-unitary? Maybe the issue is the semi-classical analysis. Maybe there are non-perturbative corrections that somehow fix this. So the question is, what does a unitary entropy curve look like? And this is known as the page curve. So the idea here is that the black hole, initially the entropy of the radiation is 0. As the black hole starts radiating, it increases. We know that eventually the radiation becomes the entire system. So it has to eventually have 0 entropy. And so the curve we know must come down somewhere. And in fact, you can show that there's the turnover, if you assume unitarity, the turnover has to happen when the black hole is evaporated half its mass. So this would be what unitary evolution would look like. And then the question is, we have these two different curves for what the radiation of entropy looks like. What is the correct curve in quantum gravity? Is it the unitary curve or is it the non-unitary curve? How can we calculate it? How do we ascertain what quantum gravity actually does? And that brings me to holographic entanglement entropy and holography in general. Are there any questions so far? All right, so a bit of a preview just as a reminder of where we're going. From the perspective of semi-classical gravity, it's hard to see where Hawking's analysis goes wrong. And it would seem that we need some ingredient from quantum gravity that would help us figure out what went wrong. if we indeed think that quantum gravity is a unitary theory, which we do. Now, what we found in these new developments in the past year is that a completely classical, semi-classical analysis can give you the unitary page curve. You can actually calculate this unitary page curve from a completely semi-classical analysis, but only if you interpret that calculation as something that's coming from quantum gravity. And I'll be very explicit about what that means later. Specifically, as something that's inherited from holography. So, what is holography? So we call it holography or ADS-CFT. We also hear it called gauge gravity duality. So holography is a duality between quantum gravity with anti-de Sitter boundary conditions, which we call the bulk, and a lower dimensional non-gravitational quantum field theory, gauge theory, which we call the boundary. So here I've drawn a cartoon. We have a d+1 dimensional string theory or M theory with ADS boundary conditions, and I've suppressed the compactified directions. And we have a d-dimensional gauge theory. There's something a little bit misleading about this picture. It makes it look like the gauge theory, the quantum field theory, is living literally on the asymptotic boundary. That's not the case. It lives on the space-time that is conformally identical to the asymptotic boundary. Yeah, Andy.
Netta, are you only going to be talking about ADS, or are you also going to be talking about black holes in flat space?
I will mostly be talking about ADS. I'll have some comments at the end about generalizations to, I can talk a little bit at the end about generalization to flat space, but for now, because for the portion where I talk specifically about holography and quantum extremal surfaces and that calculation, I'll talk about ADS. When I talk at the very end, I'll say a few words about the gravitational path integral, and in principle, that calculation you could imagine doing with, and actually has been done since then in asymptotically flat space, like CGHS.
Of course, I mean, in ADS, the black holes don't typically fully evaporate. So
I agree, and I'll talk about that as well. We're going to force them to evaporate, even though they really don't want to. So for the moment, let's focus on ADS-CFT. And normally we're going to work with the limit where quantum gravity becomes semi-classical gravity. But ultimately, this duality really is a statement about non-perturbative quantum gravity. So that is the sense in which holography can give us a lot of intuition about the information paradox, about anything that requires non-perturbative quantum gravity. One of the statements of holography, which is very powerful, is that any gravitational system is just an ordinary non-gravitational quantum system in lower dimension. In particular, a black hole is just another quantum system. There's this beautiful picture, which is certainly not mine, which I found online, and this is meant to indicate this picture is meant to show, so here we have this three-dimensional gravitational picture, we have some space-time curvature, maybe a black hole, and a two-dimensional hologram that encodes what's happening inside, what's happening in this gravitational theory. Now, the quantum field theory evolves unitarily. And this immediately tells us that quantum black holes evolve unitarily. So ADS-CFT implies unitarity of the evaporation process. Just evaporation, unitarity for quantum gravity in general. But of course, this is not very satisfactory. We're sort of being told by some deity, ADS-CFT, everything is unitary, but that's not good enough. We want to understand the mechanics of how this happens in the gravitational theory, not in terms of the boundary theory via some convoluted dictionary. We want to see explicitly how unitary evolution happens. So is ADS-CFT just going to give us this roundabout answer, or can it help us out with actually understanding the mechanism in the gravitational theory that does this?
Netta, a question?
Yeah.
The real world is not ADS.
That's an excellent point. And this relates a little bit to what Andy was saying, in that you might worry that there are some qualitative differences between ADS black holes and asymptotically flat black holes. There are two answers to this question. The first one is that actually we're pretty sure that, especially with the recent developments that I'll talk about at the very end, that all of this will apply to asymptotically flat black holes. And so we think that the insight is universal. And the second statement is, well, maybe it's not. and again, the developments at the end indicate that it should be, but even if it weren't, even if it were just in ADS, having even one instance of a situation where we can understand how black hole evolution can be unitary explicitly is so valuable that I have no doubt it would lead to significant insights about quantum gravity and universal insights about quantum gravity. So the point is well taken, but I think we can address it. So I want to mention an aside on firewalls, because really no talk on the information paradox is complete without some mention of the firewall problem. So especially if we talk about ADS CFT. Now in 2012, Ahmed Almhiri, Don Meroff, Joe Polchinski, and Jamie Soley, who were later joined by Douglas Stanford in a follow-up collaboration, they pointed out a very sharp paradox, which was elucidated further by Don and Joe, that occurs when you treat a black hole semi-classically, specifically in the context of ADS CFT. And so this generated a lot of work, and I won't go into the details of the firewall paradox, because surprisingly it's a little bit tangential actually to the recent developments. But the way in which it is relevant is that many of us, maybe not all of us, but many of us certainly thought after AMPS, after the firewall problem, that nothing short of a direct, non-perturbative quantum gravity analysis of bulk physics would reveal unitarity. That certainly was, I would say, a popular opinion after this firewall paradox was discovered. And it turns out that we were wrong. It turns out that a holographic calculation of the entropy in the semi-classical regime using purely semi-classical tools does in fact yield a unitary page curve. And if you take nothing else away from my talk, I hope that you take this away, which is that you can do a semi-classical analysis and see unitarity, if only you know what is the right ingredient to pick from quantum gravity. So this is this was a surprise, I think, to many of us in the field. So the critical ingredient here was the holographic entanglement entropy. If we just take a look at a black hole in ADS and we somehow manage to make it evaporate, and we just calculate the entropy the way Hawking did, we would get what Hawking got, which is to say information loss. So the way in which we have to insert quantum gravity into the problem is we use the holographic duality. So we don't calculate entanglement entropy using Hawking's method, we calculate it using holography. So how do we do that? Well, I'm going to begin level by level. Begin purely with just purely classical physics. We have no quantum fields in our system, we only have just classical general relativity. So this is working to 0th order in GH bar in the metric. And this is the famous HRT prescription. So it tells us that the von Neumann entropy of a boundary state rho, so this now refers to the boundary, the dual quantum field theory, is given by the area of a surface X in the bulk over 4GH bar. And I hope this looks familiar given the first half of this talk. Now, X is a particular distinguished surface. It is the minimal area surface, which satisfies 2 criteria. First, it's homologous to the boundary. Now, I'm sensitive to the fact that there are mathematicians in the audience, and when they see the word homologous, they might think in terms of simplices. I guess we're simple physicists here. By homologous, what we mean is that there exists a hypersurface H, whose boundary is the union of X with the asymptotic boundary. So this is when I say a surface is homologous, that's all I mean. And the second requirement is that the surface is an extremum of the area functional. So qualitatively speaking, or intuitively speaking, what that means is that if you take the surface X and you consider infinitesimal perturbations of its location, this does not change the area to leading order in the perturbation. So this is what we call an extremal surface, or in this talk, I'll call it a classical extremal surface. So the area of the surface of a 4GH bar gives you the von Neumann entropy of the boundary state. And an example is the bifurcation surface of Schwarzschild. So we have a picture next, yeah. So here I have Schwarzschild ADS. And this means, so this has 2 asymptotic boundaries, which means that I have the dual theory is a CFT on 2 copies of the Einstein static universe. And the bifurcation surface of Schwarzschild here computes the von Neumann entropy of the CFT on 1 of these Einstein static universes. So that is, we trace out the degrees of freedom on 1 of them, and we look at the CFT remaining on just 1 of these copies of the Einstein static universe. So it's this right one over here. The area of this bifurcation surface here computes the von Neumann entropy of this side. Now I want to go then to next order. This is the Faulkner-Lukowitz-Moldesina prescription. So with this order, this is we're going to include quantum fields on a curved background, but no back reaction. This does change, even though it doesn't change the metric, it changes the entropy formula. So now, instead of just computing the area of X over 4gh bar, we add a contribution from the von Neumann entropy of the bulk quantum fields. And if you'll recall, this quantity here is the generalized entropy that Jacob Bekenstein defined in 1972. And again, X here is unchanged. It's the same as the minimal area extremal surface homologous to the boundary. So in this picture of Schwarzschild over here, if we were to add the contribution of quantum fields, we would say that the entropy of this, of the CFT on this side is the area of this over 4gh bar plus the von Neumann entropy of the bulk quantum fields on this right wedge. Now, if we wanted to continue, we wanted to go to higher orders, we have to take into account back reaction. So at higher orders, we consider the effect of quantum fields back reacting on the geometry to all orders. And this new prescription actually involves a different surface altogether. So the von Neumann entropy now is given by the generalized entropy, again, A over 4gh bar plus S von Neumann, but is the generalized entropy of this surface chi, which is different from the classical extremal surface. This surface is the minimal S-gen surface, which is homologous to the boundary and is an extremum of S-gen. So instead of extremizing the area, it extremizes the generalized entropy. And we call it a quantum extremal surface. So an example, if you have Schwarzschild ADS and your quantum fields are in the Hartle-Hawking state, then the bifurcation surface is both classically extremal and quantum extremal. But if you imagine putting your fields in a different state, then that will no longer be the case. Another example is the Oppenheimer-Snyder-Ads. So Oppenheimer-Snyder in flat space is essentially it's a solution that we construct by essentially considering the collapse of a collapsing shell, so collapse of time-like matter. And it's, so here we have, this is a one-sided geometry. This is just R equals 0 over here. And this is the same thing, just with ADS boundary conditions. So what is the HRT surface, the classical extremal surface of minimal area that is homologous to the boundary? Well, in the previous case for Schwarzschild, we have this non-trivial topology. We had the second boundary. And so the minimal extremal surface was the bifurcation surface. But here, there's an obvious minimal extremal surface, which is just the empty set. The empty set is certainly has smaller area than anything else that you could imagine. And so the empty set is the HRT surface, the Rei-Takenagi surface of this boundary. And if you consider quantum corrections, as long as the black hole is not evaporating, you'll find that the minimal quantum extremal surface is also the empty set. So this is just two examples, and in both of these examples that I've given, the two explicit examples, the quantum and classical extremal surfaces coincide. Or if you consider, say in this case, some perturbation of the Hartle-Hawking state, you'll find that the quantum extremal surface might move slightly, as long as you're still on shell. So in both of these cases might lead you to believe that the classical extremal surface and the quantum extremal surface, well, they're either right on top of one another or they're very close to one another. And that certainly was the accepted perspective until May, when we found that it is actually possible to have a quantum extremal surface which is very far separated from a classical extremal surface in semi-classical gravity. So, and one more ingredient here before we move on to evaporating black holes. I want to parse a little bit the statement, a black hole is a quantum system, an ordinary non-gravitating quantum system. So far, all we've done is talk about the entropy. But what do we really mean? But what about the rest of the system? What is it describing? What aspect of the bulk physics is the state of the dual quantum field theory describing? And this is addressed by what we call entanglement wedge reconstruction. So that's the statement, and I've sort of started listing some of these names because they've contributed. They were sort of the first to talk about this, but there've been a lot of contributions. So the entire region. So here in this picture, we have, let's consider the right boundary, and we have this quantum extremal surface over here. Let's imagine that we're in the Hartle-Hawking state. Now, the entire region that is space-like to this, and in between this and the asymptotic boundary, so that's this entire wedge, that is what is described by this right CFT state. For the ones who prefer something a little bit more precise and mathematical, this homology hypersurface that I described before, this H that defines the homology, its domain of dependence is this region. And we call that the entanglement wedge. So we say that the entanglement wedge is dual to the state. And what that means is that literally everything in the bulk physics, the metric, the quantum field, state of the bulk quantum fields, that's all described by everything you could observe is described by the state on the boundary and the operator algebra. So that's the summary of the ingredients that we have. And now we're ready to put those ingredients together, the information paradox together with holographic entanglement entropy, to talk about what's been going on with the black hole information paradox now. So let's consider an evaporating ADS black hole. And as Andy pointed out, actually ADS black holes don't evaporate. So what do we really mean by that? Well, technically large ADS black holes don't evaporate. Small ADS black holes do evaporate, but by conservation of misery, we don't understand small ADS black holes. So it seems that we have ourselves a bit of a catch-22. Now, how do we get ourselves out of this? Well, we can force a large ADS black hole to evaporate, essentially by extracting the Hawking radiation and throwing it into an external system. So essentially, you could think of the reason that large ADS black holes don't evaporate as the statement that, well, the radiation, you could imagine you have some radiation, it makes it out to the asymptotic boundary, and then it bounces right back in, goes back into the black hole. But if we force it to leave before it can do that, then there is a sense in which we can force the black hole to evaporate. So that's the rough idea. And the method is that we couple the black hole to a reservoir, which is colder than the black hole, so 0 temperature. So here we have the bulk, and here we have some bath. The bath suggests that it's warm, but you should think of this as an ice bath. And at some point, so this here is the asymptotic boundary of the bulk. At some point, we couple these two systems and allow free exchange between the bath and the bulk, resulting essentially in the bulk evaporating into the bath. Now, note the fact that we've introduced a second system here and allowed the two systems to interact means that we can't expect that the bulk alone, the evolution of the bulk by itself, is now unitary. But what we do hope is that the evolution of the full system is unitary, the union of the bulk and the bath. Yeah, Andy?
Can this be done consistently with general covariance?
I don't see why not. I mean, we did it. We explicitly worked it out in Jacob Teitelborn, but okay, so I suppose one concern you might have in higher dimensions is about gravity leaking across the barrier, because here the bath has no gravity. It's just a CFT in the ground state. You might worry about gravity leaking across, and that is a concern. We haven't explicitly done this in higher dimensions, but in 2 dimensions it does work. Does that answer your question?
I wasn't aware that it worked in 2 dimensions.
You want to know? Sorry.
There's a boundary condition in 2 dimensions where you can couple a system without gravity to one with gravity.
Well, the point is that in 2 dimensions, all the dynamics are just in the boundary particle. It's literally you have very few. Essentially, we turn off gravity by just using the dilaton for the bath system, which allows us to. That's what allows us to do this. You could also think of this as just putting transparent boundary conditions on the asymptotic boundary instead of reflecting boundary conditions. You don't have to worry about gravitons, say, leaking across, because in 2 dimensions you don't have those. So at this point, we may expect that the entropy of the CFT that's dual to the bulk can change, and the entropy of the bath can change. But we hope that we would expect that the entropy, the total entropy, is always going to be constant. Okay, so let's take a look at what happens here. So at early times, the quantum extremal surface is the empty set. So we compute the entropy of the CFT at some moment in time. And at early times, that's the empty set if we're working with a one-sided black hole, or if you're working with a two-sided black hole, is going to be the bifurcation surface. And so the area of the empty set is 0, and we get just the von Neumann entropy of the CFT at this time is equal to the von Neumann entropy of the bulk. So it's just the entropy of the quantum fields evaluated on this slice. Now, as the black hole evaporates into the external system, the von Neumann entropy on this bulk slice is going to grow. And after the black hole has evaporated half its mass, a new quantum extremal surface with a smaller generalized entropy than the empty set appears. So now we have this new quantum extremal surface that's sitting here, is fairly close to the horizon. And the generalized entropy of this, so the area of this of a 4GH bar plus the entropy of that, is going to be smaller than the entropy of the empty set. And the reason for this, you can sort of see it here, is that we have a lot of entanglement between this and the Hawking radiation. So by excluding that region, it sort of more than pays for the price we pay with A over 4GH bar. And this jump in the quantum extremal surface from, in this case, the empty set to this, or in the case of the two-sided black hole, is going to be from the bifurcation surface to a quantum extremal surface that lies close to the horizon, actually results in a decrease in the entropy. So the entropy increases until this jump, and then it starts to decrease after the jump, which gives us a unitary page curve. So with the quantum extremal surface prescription tells us the entropy increases and then it decreases. And so using just tools from semi-classical physics, we only needed to calculate things perturbatively, we can recover the page curve for unitary evolution. This is literally the curve that we get. And so let me actually pause here and ask if there are any questions so far. So these are the developments from last May. If there are no questions, let me move on to things that followed quickly after. So remember what we talked about the entanglement wedge as the part of the bulk which is described by the CFT. So in this case over here, the CFT state over here is going to describe the region that's between this and this CFT moment in time. So this slice over here and its related width patch. So what about the rest of that? Well, let's think of, if we really take entanglement wedge reconstruction very seriously, then we may be tempted to say that we extracted some part of the bulk, we extracted the radiation, and that is what is dual to the rest of the bulk. In other words, sorry, the entanglement wedge of the radiation is the region behind the quantum extremal surface. So this was a proposal that was put forward by these people, alluded to earlier by Hayden and Pennington. And this statement is essentially the statement that the radiation contains the information about the black hole interior, that it carries it out, which is exactly what we would want to see in unitary evolution. So let me just quickly summarize this. So the story appears to be quite beautiful. We are able to reconstruct the page curve, and we're able to see that the Hawking radiation carries information out using nothing more than a semi-classical analysis, but using the fact that, or using the assumption that this semi-classical analysis is computing an entropy. So what happened here? We used this formula for the boundary entropy. So this state here, rho bulk, that's the Hawking state that we put in. We used the entropy the way that Hawking would have calculated it. And this would have given us, this by itself would have given us the Hawking answer, a non-unitary answer. Now, this thing over here though, if we correct it with the area of chi over 4GH bar and solve for chi correctly, then this entropy evolves unitarily as predicted by quantum gravity. And this is rather surprising and in some sense, in my opinion, miraculous. Now, the only place where quantum gravity could have intervened to give us this unitary evolution is in the interpretation of this quantity as the entropy of the radiation. That is the only place where quantum gravity would have been able to put in an ingredient that would have allowed us to get unitary evolution. And so clearly, if we want to really understand how this happened, we have to ask, what is the microscopic physics that justifies the quantum extremal surface prescription? What is the reason that this is the correct way to calculate entanglement entropy in the CFT. And so how did we do this? And I apologize, this bit is a little bit technical, but I think it's sufficiently illuminating that I still wanted to include it. So here they have the slew of different acronyms for the different prescriptions in order of generality. And these can be derived from the gravitational path integral. So let me spend a couple minutes on that. So here we have the von Neumann entropy, and we can write it just in terms of this, this limit. We haven't done anything other than just rewrite it as a limit here. And this object z sub n here, this is the partition function defined by n copies of the certain boundary conditions. So the partition function in semi-classical gravity, we can calculate it via saddle point approximation. So this is the approximately e to the minus I grav, although technically the partition function is a quantum gravity object. And this here, I grav is the classical gravity action for a single copy of the system. So Zn is going to be given by classical gravity action for many copies of the system, many copies of the boundary conditions. And again, there's been a lot of work on this, and I've listed this in chronological order. So you may have noticed that I put an I here rather than an S, and really what's going on here is I'm working with Euclidean gravity. So this is really the Euclidean path integral, and while you can talk about what happens with the Lorentzian path integral and do some Schrödinger-Keldysh contour, I think the picture at this point is still clearest when we talk about Euclidean gravity. So we work with that for now. So normally we do this in Euclidean gravity, which, just to give you some intuition, means that if we're working with Schwarzschild, we do a t goes to I tau continuation, and we get this geometry that looks like the end of a cigar. And tau here is an angular coordinate, which is periodic with the temperature. So this is related to the temperature. Now, so this is just the rough intuition behind this Euclidean gravity action. So we're going to continue in Euclidean signature. We have this partition function, which is approximated by this by a saddle point approximation with the classical gravitational action. So again, the Zn is the partition function approximated by the classical gravity action for n copies of the system. So how do we work with this operationally? So operationally, what we do is we set boundary conditions for n copies of the system. We then use the Euclidean gravitational action to solve for the Euclidean gravity solution that dominates the saddle point approximation. And then we use this approximation of z sub n to compute the von Neumann entropy. So as an example, we're working in 1+1 dimensions. Here we have boundary conditions. We can solve, we solve with the Euclidean, we fill this in. So we filled in this circle with the Euclidean action. And then we can analytically continue. This would give us this top half of the Lorentzian black hole. So this is how these three are related: the boundary conditions, the Euclidean solution, the Lorentzian solution. So what happens with this Zn? Let's compute Z of n equals 2. That means that we take 2 copies of these boundary conditions. So for the 1+1 dimensional black hole, it's just these 2. Now the complete answer to what Z of n equals 2 is actually obtained by doing a quantum gravity calculation, as I mentioned before. But we can also do a saddle point approximation and look for the saddles of the classical Euclidean action. And in this case, there are at least 2 of them. So this is the way that we can fill in these boundary conditions. So we can either fill them in separately. So this gives us 2 copies of this black hole that we saw before. So it's just 2 separate copies. Or, as was shown by these two groups, and was actually discussed in earlier papers as well in the 80s and more recently by Maldacena and Maas, you can fill them in with a connected geometry. So I just want to make it clear that these 2 are 2 qualitatively different objects. This first one over here, if you analytically continue to Lorentzian signature, you get just 2 copies of 2 Einstein-Rosen bridges, 2 spatial wormholes. This thing here is actually what we call a Euclidean wormhole. So this does not continue to a nice Einstein-Rosen bridge. This is not a spatial wormhole, but a space-time wormhole. It's a very odd sort of object. But it's rather remarkable. So in our case, the quantum extremal surface and its generalization to include the radiation and not just the black hole entropy, this can be computed directly from the gravitational path path integral in this way for certain toy models. And remember there was a jump in the quantum extremal surface. It went from the empty set to this non-empty surface, or from the bifurcation surface to something near the horizon. This occurs due to a switchover. You can trace it back to a switchover in the dominating saddles from the disconnected to the connected Euclidean wormhole. So we can trace back this exact switchover, which is what gives us unitarity, which is what's responsible for unitarity, at least in that calculation, to the switchover between these two saddles. So this is telling us. So let me actually pause here for a second and say that there's no reason why the gravitational path integral would have to be done in ADS. We could do this also in flat space if we wanted to, in asymptotically flat space if we wanted to, which is the gravitational path integral in general. We don't expect is particularly special to ADS. So indeed, the gravitational path integral has a history of knowing more than it has any right to, not in ADS CFT necessarily. So even though it's a purely semi-classical construct, it can, for example, compute the entropy of the Schwarzschild black hole, given Hawking calculation. And this was indeed verified later, done explicitly by microstate counting by Strominger and Waffe in string theory. So the Euclidean path integral, in particular, the gravitational path integral, really appears to know a lot more than it has any right to. And including the fact that there's a switch over here that takes care of unitarity. So how did the gravitational path integral know what the unitary answer is, given that we're calculating it just using semi-classical physics? Which leads me to the black hole information paradox tomorrow, trying to be a little bit of an oracle. So the gravitational path integral, as I said, is quite clever. It has this new cell that dominates at late times, which actually raises some, you could say disturbing questions, or you could just say interesting questions. So the fact that the solution is a connected Euclidean wormhole allows for potentially non-trivial correlations between the n boundaries, these n copies. But really, these are n copies of the same system, and independent copies of the same system. And it doesn't immediately seem possible to have this happen in a single exact theory. So it seems that it seems like there's some kind of a potential problem in including these connected wormholes, even though they give us the right answer for the entropy. Now, I would say, at least maybe I shouldn't say we, speaking for the entire community, but at least I would say I'm pretty sure the cell actually is legal and we're supposed to include it. But it raises the question of what exactly is the path integral calculating? The only example where we actually have an exact understanding, or have some understanding at least of what's going on here, is in 2D dilaton gravity. And there what it's doing is a disorder average. So it's averaging in some sense over theories, over couplings. And in that case, it's okay to have these connected wormholes. But it's not clear what this means in general, how it's supposed to work in higher dimensions, or for example, in the case where we have ADS5 cross S5, which is dual to n equals 4 super Yang-Mills, that's a single theory, and it's a single exact theory. And it's not obvious how this is supposed to work in that case. Is there maybe some other contribution that cancels out these correlations, or is there some approximation that we need to do? I would argue one thing is clear, which is that we have pinned down a key ingredient in the resolution of the information paradox, the gravitational path integral. We have to understand what exactly it is computing and why it is so smart. That is something that it is critical for us to understand in order to leverage everything that we have learned from ADS CFT and from this recent work and from decades to get through to resolving the information paradox. So the current state of the information paradox is that we haven't solved it yet. There are a lot of very interesting questions that we should be working on, and many of us are working on. What is the entropy? What entropy is the gravitational path integral actually calculating? So can we calculate it directly without going through the path integral? Can we actually do that calculation? And maybe on a more physical level, what does an observer outside the black hole actually measure? If we could make arbitrarily accurate measurements and had an arbitrarily good quantum computer, would we, upon feeding these measurements to our quantum computer, find a pure state or mixed state? What would we actually observe if we could collect all the radiation? Is the path integral doing an averaging of some sort? What is it averaging over? Is the semi-classical limit of gravity just an approximate description of some ensemble? And one thing that I would personally very much like to understand is what exactly are those corrections that Hawking didn't include, that if we did include, we would get a unitary answer. It's a little bit related to my first point of how do we calculate this thing that the gravitational path integral is calculating directly without going through the path integral. And so I hope I've given you some food for thought. And with that, thank you for your attention.
Thank you very much, Netta. That was very interesting and exciting to hear. We have time to work on. We have time for questions, so please raise your hand. Maybe I should ask one question. What is the special property that a horizon brings to the problem? In other words, suppose we had a box and we would have Bob and Alice and throw Bob into the box, and just the box is sealed. We don't know what the whereabouts of Bob. Would that behave like a horizon, or is there something really about the microphysics of a horizon that makes it special?
Yeah, so that's an excellent question. So I'm going to give two answers to this. Maybe the first one is a bit of a cop-out, but the second one will hopefully be a little more satisfying. So the first answer is that you could say that what makes the black hole in this case special, the existence of a horizon, is that it collects these the partners of the radiation, and then it disappears from the space-time altogether. So if you had just collected things in a box, as long as the box still exists, you can always take at every moment in time, every Cauchy slice you would take would always go through the box, and you would never encounter a violation of unitarity, because if you consider the entire system, the box never leaves the universe, it never leaves the entire system. What's special about the black hole is that, and the horizon, is that once something goes through it, and if the black hole evaporates, it's a mechanism for things to apparently, at least from semi-classical physics, just leave the system altogether. So that's the first, yeah.
Maybe it's related to the existence of a singularity, because eventually this material, I mean, in the rest frame of that material, it ends up in the singularity, right?
Yeah. Yeah, so, well, we don't run into this problem if the black hole doesn't evaporate, though, because if it doesn't evaporate, then every Cauchy slice that you take you will always be able to include those objects that went into the black hole. The problem is if it evaporates, and yeah, it went through the singularity, now the singularity is gone. So it definitely has to do with the singularity, but it's important that the singularity eventually disappears, because then there's no Cauchy slice that you can take that goes through the singularity. There is, I would say, your question is also, the second thing that I was going to say is that your question is also related to the firewall paradox, which I would argue we haven't really resolved. So everything that we've done so far is based on entropy and entanglement entropy. And the original firewall arguments did involve, were various entropic arguments. But there's an interesting one, which is due to Malov-Polchinski, which doesn't actually invoke entanglement entropy, and really does an analysis of, well, it does an analysis of what's going on around the event horizon. And I don't think that what we have said so far has bearing on that part of the paradox. So I would not say that this is one of the reasons I say we haven't really resolved either firewalls or the information paradox yet.
Thank you. Questions for Netta? Andy.
You have to unmute yourself.
Oh, Andy, you are muted.
I'm muted.
Yeah, I've always felt that a good paradigm for what one would like to do is what Boltzmann did. So he made a sharp assumption. He assumed that matter was made of molecules. It's a sharp, well-defined assumption. And once he made that assumption, he could derive thermodynamics from statistical reasoning. But it was an assumption about some kind of assumption about microphysics. He didn't assume the periodic table. And so understanding black hole the information paradox using string theory is like assuming the periodic. It's too much to assume.
Yeah.
We'd like a a less precise assumption. Now you're sort of getting to that. You know, that sort of this, if you assume that the entropy is the quantum extremal surface, but that's a little bit too specific of an assumption. That's a little too close to assuming the answer, I guess. So, and somehow you want to say something like you want to assume holography, but what does that mean to assume holography? Could you comment on that? There's some assumption you want to make about the nature of quantum gravity, and then from that assumption, you know, resolve the information paradox, and without assuming string theory and duality and all that stuff.
Yeah, I agree. Or at least, I don't know if maybe resolve the information paradox is not realistic, but maybe I guess I'm young and maybe I should have high ambitions. So a couple of things. So first of all, I would say that until recently, it was not at all clear that assuming quantum extremal surfaces, that prescription is similar to assuming the answer. In fact, I think Aaron and I even had some statement in our 2014 paper about quantum extremal surfaces where we said that essentially the quantum extremal surface is always going to give you more or less the same answer as the classical extremal surface. So so I think this was actually quite a surprise. It's making that assumption and getting something that's consistent.
No, I agree, but it's closer to assuming the answer.
But now we've done that. So where do we move from here? So I think that the thing that we would like to maybe assume is not the word I'm looking for. One thing you could try to say is, let's assume that the quantum gravity partition function is well approximated by the gravitational path integral. And what I'd like to get out of that is then to ask, what does that tell us about the gravitational path integral and what it's doing and what it's calculating, and why that is sufficient to resolve unitarity problems? And in particular, why does that allow us to include these Euclidean wormholes? Because I think understanding the type of disorder averaging that the gravitational path integral does, if that is indeed what it is doing, is critical for understanding why it knows so much, which is, I think, essentially the reason that that it approximates a quantum gravity answer. So if we assume that it approximates a quantum gravity answer, how much knowledge do we get out of that as far as understanding what it's doing and why it's right such a large part of the time?
Is that that's a nice thing. Assume that the quantum gravity path integral is infinitely wise, and is that disorder average related or the same thing as the averaging over super selection sectors that comes out of summing over wormholes, or is it something slightly different?
You know, I honestly am not sure what type of disorder averaging we're looking at, except for the case when we work with SYK, where we know exactly that we're just averaging over the coupling. I can tell you that so here's a sort of a wild guess, which I have nothing to back it with, but this is just a potential hypothesis that I think that it's quite possible that semi-classical gravity is a limit of several different exact theories. And when we do this semi-classical approximation, we're averaging over those theories. So for example, n=4 super Yang-Mills, I think, is described in quantum gravity in the bulk. But when you take the n goes to infinity limit, then there are potentially other theories with the same n goes to infinity limit. Those are not actual field theories at the end of the day. And potentially what is happening is that we're averaging over those. I suppose that I don't have a good way of testing that right now, but that's not a not inconsistent working hypothesis.
Okay, any other remaining questions? If not, I wanted to thank Netta again for responding to our eagerness to learn more about her research and related advances in this field on a short notice. Just a few weeks ago, we asked her and she agreed. And This is our last BHI colloquium. We look forward to starting it all over again in September. We shall see if we come back to our corridor or not by then. Probably the university will announce what will happen around the beginning of July. So stay tuned for that. And also join us tomorrow. We have a special colloquium with Stephen Wolfram on his new theory of everything. See you then. Bye-bye. Stay safe and healthy.
Thank you for the warm reception.
Thank you, Netta.